Hey YouTube, it's Dimitri, and today we're going to talk about OPM. So let's just write this out here. OPM is going to be ongoing performance monitoring. And ongoing performance monitoring is just how we manage the risk behind our models across time. So basically what we're going to do is we're going to build a model, we're going to address the risks that we have with that model, and we're going to choose different metrics to monitor that model as we use it. And as the model starts to fail, meaning some of these metrics here start to get out of whack, then we'll know that we need to build a new model here. So this is the purpose of ongoing performance monitoring. It's to manage risks. It's to warn us that we have an issue before we have a serious issue, and it should give us time to replace these models. Now I'm going to put a massive warning here. OPM is not a replacement for crappy model development. I see this constantly. I will talk about this probably in another video. There are financial applications require models to last for long periods of time in most scenarios here. You can't just build crappy models and then go, okay, but I have ongoing performance monitoring and it's just going to catch everything. And then as soon as this model sucks, we'll replace it. A bad model will fail very quickly. This is why I emphasize heavily the robustness testing in machine learning models, because that is what we do in statistics. So just as a warning, don't use OPM as a crutch and think somehow if you have OPM, it will fix your problems. Bad models will fail quickly. OPM won't work. So the two pieces that we want to address here with OPM is going to be what metrics should we use? And then the second question we're going to have is how do we set our RAG, which are going to be thresholds. Now, RAG is what a lot of the banks call this. It just stands for red, amber, and green. And I'll talk about this here in a second. But let's dive into how do we select the metrics? Also, how do we select the frequency of testing? Okay, so one is going to be metrics and frequency. And this is a challenging piece because it varies for every single model. So there are classifications and groupings of model, and you'll figure these out as you go. But most models, they want to look at things like accuracy. So let's just start with accuracy here. Again, you might choose different metrics for different things. So I was modeling something with a colleague of mine. It was the amount finance. And this is going to be the amount of a vehicle. So the prediction of this is going to be some dollar value, let's say from zero to, I don't know, $100,000. And a metric that we absolutely love to use for this is going to be the mean absolute error. The reason that we love to use MAE is because the business understands this. This is the average dollar error for the model. So people can interpret this very quickly and very easily. So when you have things like dollars, it's nice to use metrics that are easy to interpret. They're not just going to be like a numerical piece here. I'll make another note as well. I'll put a little star over here. Model selection is complicated, so it is dynamic. It is a challenging piece in itself. So I'll put complex here. But more specifically, one thing they don't teach in school for some reason is that it is comparative. And what I mean by this is often you will have some ridiculous business problem with no simple, easy solution here. And we're going to build a handful of models here. So I don't believe in building 1,000 models like the crazy data science community. We carefully choose and select models to solve the problem. We execute with precision. We make these models the best they can be for the types of models that we have. And then we look at a variety of different metrics for comparing models here. Again, this is going to depend based on very specific types of models here, but pick the best possible. So let's say best possible model here. And you're gonna weigh a bunch of different things like fit or accuracy, robustness testing, and then I'm gonna put in here just business preference. And what I mean by this is sometimes it's not a bad thing to either overpredict or underpredict, but the opposite has very devastating consequences here. So think about a business, I don't know, for like investing here, you're trying to figure out what stocks to buy and sell. You would rather overestimate your losses and your risk in this scenario than underestimate them. Because if you underestimate them, that could be massive consequences for you. Whereas like if you misprice and you happen to make a bunch of extra money, like no one's going to complain about that. But back here to different types of models. So this is amount financed here for vehicle valuations. So I'll talk about a little bit about that. The second piece is maybe we're doing some sort of probability. So let's say, I don't know, the probability of charge off, which is a common one. We're going to predict something between 0 and 1. So that is going to be a very, very small window here. So probabilities go from 0% to 100%. You would not want to use MAE here. It would make no sense. Your values would be like 0.003257. And then the question is like, what does that mean? Like we can compare, so we can go up here and do comparisons on models, which is a good thing to do. But it's hard to interpret. So often we'll use something like mean percentage error. So that's a really good metric to use in this scenario here. For these sorts of problems as well, we often classify, so our target or dependent variable will look something like this, where it's just binary and there's zeros and ones, meaning, you know, this is so for charge-offs, this is a good customer who did not charge off. And then the ones here are going to be what we call bad customers, in the sense that it defaulted, it wasn't a good loan. And so when you do things like this as well, you might have metrics. So let me get another screen. You might have metrics like AUC. So this is going to be called area under the curve. And I'm not going to get too much into the specifics of this. But this is a line at 45 degrees. You have some sort of line like this. And the area underneath of this curve here, so this area in here, the sum of this area, technically the sum of this area right here, this value represents separation of your goods and bads. So this would, be 0 and 1. Now, if your value, so for most metrics here, they're going to be comparative. So you're looking at different models, which model is going to be the best. Now, again, as I mentioned, it depends, which I know everyone hates to hear, but for metrics like AUC, a value of 0.50, so this 45 degree line right here, that we were looking at, that means it's a random guess, because you have two scenarios. You have 0 and 1. And if you just randomly guess about different customers, you're going to automatically get 50%. So we need to have a value greater than 0.5 in development data, in validation data, and out of time data. For all different scenarios here, because if your curve is on the line or less than the line, randomly guessing is actually a better decision than using the model here. So there's not always going to be some sort of metric with an absolute value, but there are some cases. The other note I'll put here too is industry standards. And there are often industry standards about what things should be at. So again, industry standard, even for like AUC, will depend on the firm. Is it prime, subprime? Like some populations are easier to predict than other ones. Again, we'll look at the metrics here in general, but something like 7.5 is decent. That's pretty good. So put a thumbs up, arrow up. Anything that's going to be less than, 0.7, you're not so great. Again, it depends on the problem. Some problems might have something that's even lower here. So what I want to get at here with the metrics is that you need to pick metrics that actually mean something to you and to the model here. Again, accuracy is what we mentioned here, fit. You might have other things, for example, like robustness testing. So I'll put a little another note here. For time series, I really like root mean squared error. As I mentioned, for dollar values, I liked MAE. For percentages, I like MPE. These are just personal preferences. Robustness, though, can come in the form of residual analysis. So residual analysis is going to be different characteristics or tests that rely on the residuals here. So are they, are the expected value of your residuals equal to 0 is going to be an assumption for many, many models. You can monitor this, okay? Another piece here we're going to talk about in more depth a little bit. It's called PSI, which is Population Stability Index. You can do Population Stability Index for anything, any type of data, but you might also do your residuals just to see how they are kind of moving and changing over time. It gives you a little bit of a sense, not just on the accuracy of the model, but of the robustness here. And I'm going to stop right there. We're just going to look at accuracy and robustness for these sorts of metrics on an overall model perspective. Now, you're going to have things that are going to be very specific to a type of risk. So what I mean by this is it depends. It depends on the types of models you're using. It depends on the structures. It depends on the risks identified and the data issues identified during the model development process here. If you have something, let's say you have feature importance here. So in statistics, this is just your contribution of a specific variable. If you normalize, so if you have OLS or some sort of regression here, if you actually normalize your data the beta coefficients in the model will actually equal the importance here. Now, I don't encourage you to use this for your actual model specification, because the actual beta tied to like a dollar value or a very specific variable, the definition has a meaning, which is easy to interpret. If we start normalizing things, often it causes issues here, but you can just do like a quick analysis where you normalize it and refit it real quick. Same data, same structure, everything, don't screw with any of that. And then you can look at the importance based on that. You can also use walled chi square values to look at this. This has to do with importance and meaningfulness of the model. But hopefully you have some sort of chart here where it shows you, like, I don't know, there's feature 1, feature 2, feature 3, feature 4, feature 5, and it keeps going out. You might be really concerned with the stability of like the first 1, maybe 2. Let's say this drives like 80% of the prediction here. And if it does, we might want to keep a really close eye on just these 2. Like if the other ones go haywire and wonky, it doesn't really matter. But risk-wise, this is a really big risk for the model in itself. And so what we might do, as I mentioned before, is we might do something like PSI. Instead of the residuals like we talked about here, you'd have PSI of, I don't know, let's look at something like PTI. So price to income, say something like that. Or it could be something, I don't know, like GDP, or it could be whatever's in the model here. But you can use things like PSI to monitor the most important features of this model. Now, you might also have a variable that's, I don't know, like maybe like down here, and it just might be really unstable. But for some reason, like there's a business requirement, like the business themselves, they demand this variable be in the model, and they think it's critically important. Again, if it's unstable and they require it in the model and it makes the model work really well, you might do something like PSI where you actually monitor and kind of keep track on that variable here. So other examples of this might be if your model has heteroscedasticity. Now, I'm going to make a note here because someone's going to point this out. You think this is spelled with a C. I spell it with a K. I know. Many people spell this with a C. That's how like the most common spelling is. I learned it with a K here, so we use a K. Anyways, if you have something like heteroscedasticity, you can look at different types of tests for this. There are different types of tests. So you can use tests and you can rerun them on the residuals or refit the model. So another thing you can do is refit. And you can check, for example, like in stats models, p-values, just to see how the model's kind of handling. So you can check p-values and you can check your beta coefficients and just see, is there a sign change? So is it positive? Is it negative? How much are the coefficients moving by? Again, you're going to have spikes in data here. And that leads me to the frequency of monitoring, which we talked a little bit about, or we mentioned we're going to talk about. So frequency of OPM. So some of these metrics, it doesn't matter. They don't mean anything when you add a few data points here. So think about something like we talked about, mean absolute error. So this is going to be the average absolute error. So that's your residual here. And residual is going to be your actual minus your prediction. And imagine you have like 100,000 data points, and this is going to be an average of 100,000 data points here. And imagine you add on, I don't know, 5 data points. So you have 100,005. It's an average. Adding 5 is going to mean nothing to you. Okay, it's not going to move the metric. So if your MAE is like, I don't know, say $1,215.12, adding 5 data points might move it to $1,015.13. Like there's not enough data with 5 data points to move it. So you would never model something like loan originations daily. It just doesn't make sense. Okay. So in our example here, if we're doing like loan valuations, and let's just say we're doing, I don't know, amount financed for a vehicle. In this case, we might do something that's either like monthly, depending if you have enough volume, or you might choose something that is quarterly, or you might do something that's like semi-annual, or you might do annual. Now, that being said, if you're going to be doing something that's like trading related, you might do something that's like daily. It might even be like hourly. It depends how much data is coming through that model. So if you're pulling nanoseconds through, you could go into hourly and it could mean something. But for most things like banking and most fintechs and things like that, looking like at quarterly is probably the best. Monthly, I would argue, has a case if you have enough volume. Semi-annual and annual often is too much time. So it depends, again, on the model. If you're doing something like CCAR, which is the Comprehensive Capital Assessment and Review, there's also something called HCR or HCAR, Horizontal Capital Assessment Review, whatever that one is now for the small banks or smaller banks. Again, you're going to be using GDP, unemployment, all that, and it is going to be monthly data. It means you have 12 new points per year. So again, your development data set isn't going to be 100,000. It might only be 120 data points. And if you add 12 new data points in, right, that's going to be 10% of your data. So that's going to move that metric. That's going to move your MAE or your mean percentage error, or it's going to move your root mean squared error. Like whatever metric you're using, you need to think about how much data it's going to require to make something meaningful here. PSI is the same thing. So as I mentioned, PSI is great. It is wonderful. I absolutely love it. You can use KS as well. It's another metric for modeling these or monitoring movements. But what you're going to look at with these again is how much data is going to be required to move. That is critical. Okay. You need to think about that for the frequency of your monitoring. You also need to think about something else I didn't mention, and that's going to be resources. So how many employees do you have to do this, right? If you have 1,000 models and you have, I don't know, 20 employees, you probably could do it. It's a little stretch maybe, but again, it depends how much time it takes to get data and if you have systems and automations and everything else. So that is the frequency. You pick frequency based on how much movement you're going to have here. You're going to have a little bit of a judgment here. You can always you can test these things. So you can add 10 new data points. So if you have like your development sample, you can slice up like your validation or your out of time and add a few in and see how that works. So now we have some table here we're going to have. So I'll put this on this page. Let's say we have our MAE, our PSI for variable 1, and our PSI for variable 2. And now we've come to the conclusion we are going to do the frequency here for all of these. You could split them up if you wanted, but typically they're all going to be done the same. We're going to say quarterly. And now the piece we're looking for here is going to be our thresholds. So we're going to have red, we're going to have amber, and we're going to have green. And so now the question we need to answer is to finalize this. Since we have our metric, we have our frequency of monitoring, we just need to figure out what are these thresholds going to be. So some of these are going to be industry standards, like I mentioned for AUC. I like to use 0.7 as what we consider like anything that is going to be greater than that or equal to that is going to be green. Anything that is going to be between 0.6 and 0.7, again, not inclusive there, but inclusive there. This is going to be amber. And anything less than 0.6 is going to be red status. So what does this mean? You need to come up with action plans over here. So we'll say action plans for each threshold. So common one is, there's green, we do a thumbs up, everything's going good, no action required. So no action. Amber is going to be like something's kind of fishy here. So we need to report this. So report typically to the head of what's called model risk management or validation here. They're going to get involved. They're going to look at this and say, it's going to be the model risk management head. It's going to be the managing director. And then it will be probably the developer. So whoever the employee was that did development, they'll all put their heads together and look at this and go, are we hitting enough thresholds? Are we not hitting enough thresholds? So for example, if it's amber for 1 quarter, maybe it doesn't look too bad. Maybe we're just barely over. So maybe in this case here, like in this example, maybe we're at 0.69, like we're right on that threshold. So we're not going to worry about it too much and we're going to wait. So we'll make a note and record that for, risk management purposes, what we did and the decision made. And then if quarter 2 comes and all of a sudden now it's dropping into like 0.62, like we need to know why is this happening? And then we'll do an action plan and dig through that. And then typically if it's going to be red, I don't know, I'll put a little light bulb here with like light coming out. This is panic. This is like all hell's breaking loose. Something's wrong with the model. It's not working. We need to take action right now. These typically then get reported to committees. So there are usually a bunch of risk committees in banks. But again, at this point, like this typically warrants, like a redevelopment. But typically what you really need to do here is figure out why. Like what's happening, what's failing, why is it failing? Jump into action, make decisions here. So you need to have these action plans written out, documented, and recorded. Regulators love to see this. But you're going to come up with, this is what we call, like an industry standard. And again, these are my industry standards because I worked in subprime for so long. I have no idea what the prime markets are. Different firms are going to have different opinions on this. Now, the other way to actually do this is the technical way, and I'd expect you do this as well on top of industry standards here. When you develop a model, you have a development data set. So in the ML world, this is called training. So this is your training. Let's say this is 2010. And let's say this goes, I don't know, to 2018. And then you're going to have something which is called validation. You don't have to have this for stats. You can just have development and out of time, which you'll see here in a second. But we also call this validation in the machine learning realm. And then finally here, you're going to have what we call out of time. So it has to be out of time. You have to split on years in finance. You cannot do out of sample, which is just like taking 10% of this as an out of sample and then taking like, another 10%. So this is out of sample. This would be validation. So this would be like 10% of all the years. And then finally you'd have your final one. It should be like your, training or your dev data. And I don't know, say this is, your other 80%. You can't do this in finance. Please don't do this. Because this blends all the time trends and issues with time across the whole data set. And so anyways, back to this, in the machine learning world, this is called testing. Now, what you're gonna wanna do here is we have our frequency. So we pulled up, we're gonna use quarterly. What we're going to do, so when you develop the model, you already know your metrics like your MAE for dev, your development data. Let's say this is like $1,200. And you have your val for the same thing. Let's say this is like, I don't know, $1,250. And let's say your out of time is going to be, I don't know, $1,300. Now what we're going to do is we're going to split some of this up into quarterly data here. So what we're going to do is split up dev, and I usually just use the dev piece of this, but we take our metric, which is going to be MAE, and we split up dev into 10 to 12 quarters here. So again, if you're using quarterly, I would err at 12 because you're looking at around, 3 years. So you'll create some sort of table here, like, 2017. So that's that last year here. And you'll do, quarter one, quarter two, quarter three, quarter four. And then you'll do, 2018, quarter one, quarter two, and so on. And then you'll have your MAE here, and you'll have a bunch of values that you'll plot all out here. And you'll want to plot these out and see what they look like. So they look like something like this. And this will be your MAE for, 12, 18, 24 quarters. I don't know, whatever you've got. And then you'll use this to figure out how you're going to be setting your thresholds here. So if your threshold, you decide to put your threshold, your green one, right here, and this is your MAEs, this is a bad threshold because you never breach it. Good thresholds should be set such that you will occasionally touch or bump it. So this right here, this is bad, okay? No ambers or green or reds, right? Too loose. Your bands are too wide. Now, if your MAEs are going to be, again, like this, something like this, and you set your threshold here, right? They're all going to be red. This is bad. Don't do this. This is too tight. So we had too loose, too tight. Now, if we had something that was like here, this is just right, okay? This is good. This is great. This is absolutely stunner. This is what we want because we want to see that, where we set the thresholds, we're getting some action. So that might be your threshold for the one, and let's say you have another threshold that's right here. So what we're saying is this is going to be a red flag. And there's probably like 2 in here. And you'll want to look at data too. So what is the time here? right? Is this a financial crisis? Is this where inflation hit, right? We're looking at these sorts of things. Is this where the Ukraine war hit? Like, you're going to want to look here and figure out why this is occurring. And then it kind of gives you the warm, fuzzy feeling that, okay, I did this correctly because we're seeing flags and warnings where the thresholds are. So this would be the threshold for red. And then these points in here, which are hard to see, there's some here and some here. These would be amber. So let's say, I don't know, we had 12 data points. So that's our example here. So 12 quarters. Let's just say, you know, red was 1 time and amber was 2 times. And, you know, that's out of 12. So that's, you know, out of 12, if we have, you know, 1 red, that's, we'll just say 10%. And if we say 2 times for the other one, you know, that's, it's a little less than 20%, but you know, it's kind of in there. But these are pretty good metrics here. So you need to judge these. These are not just a science. This is an art. We built models, which is part science, part art. We picked the best model possible that we could build. It's kind of an art piece of setting metrics and judging that. And then when we went back to this sort of framework here, we did some testing. We did some quarters. Again, I developed the development data out into quarters and tested it. You can add in now your validation and you're out of time because you have finally selected the model. You're just doing metric fitting here. But check these different things to get a plot for each of these. And like I said, so let's just say, you know, amount financed here was our example. Our MAE, let's say anything, you know, less than our $1,200 range. That was awesome. That was perfect. For amber here, if it's going to be between, I don't know, let's say $1,000 in the 1,200 here. And then anything that's going to be less than $1,000 in this example, we could say is absolute terrible. Like the model's failing. We looked at our charts. There were only a few cases where that's ever happened. And again, we want this to be a risk like metric that's going to tell us something in life. So for something like PSI, if I remember off the top of my head here, anything less than 0.1 is typically good. Again, this is going to be based off of, you know, industry standards here. But again, you need to look at your data. You need to figure out your problem. These might not be realistic at all. You might have to make them wider. That's why we do the charting and the plotting here. Anything that is going to be, you know, between 0.1 and 0.2, that's going to be amber. Like we need to really be looking into this. And then anything that's going to be greater than 0.2 is going to be red. Again, you might have different thresholds for different variables in here because you did different testing. If you have industry standard ones, you might just say, you know, do the testing to make sure it works correctly. But you would go back through here and look at these sort of metrics. Anyways, I hope you guys learned a lot about OPM setting here. So we, you know, figured out the metrics. It's specific to the model. It can be overall metrics like accuracy, robustness testing, and residual analysis and all that. It can be very specific into very specific variables that are driving the model. So we look at those characteristics. How stable are they? How are those variables moving with time? We can monitor those specific variables. And then frequency here, that is going to depend all on, you know, how much data is coming in and out and what's going to move those metrics, because you want a metric that's going to get moved. And then again, setting the thresholds here for red, amber, green kind of structure here. You have to do testing. That's the absolute best way to do it so you can figure out where you're at. I have been at firms where they have struggled and set thresholds that have been green forever, and then they readjusted them and then they're red forever. And then management's frustrated, validation, development, everyone's upset and frustrated. And there's really no reason to be. There just wasn't this planning where you segment your database on the frequency and check to make sure that one, your frequency is correct and it's moving the needle. And two here, that you can figure out where you should draw the lines for red, amber, and green. So anyways, I hope you found that helpful. Don't forget to like, share, and subscribe. And as always, until next time.